started the second half of the quarter. And we talked about Newton's law for a fluid, which is, if you look at this, we tend to divide through by density, so we're looking at acceleration, and its acceleration following a parcel equals the forces that are on that parcel. And in that sense, it is pretty straightforward. Then we went through all the forces on a parcel of fluid. Gravity, I hope, is pretty straightforward. Pressure, we learned about the pressure gradient, and then we used that idea over and over. We talked about some of the balances, like hydrostatic, the hydrostatic balance between the pressure gradient and gravity, the vertical pressure gradient and gravity. We talked about viscosity, and we call that term sometimes friction. We talked about rotation, the two effects of rotation. These are really, really cool movie. You should watch again. This is the coolest movie of all. This is the nerdiest movie I've ever seen in my life. And we talked about the Coriolis force, and we talked about the centrifugal force. The centrifugal force, for us, it's so easy. I never think of it ever, except for when I present this, is that it's absorbed into gravity, and now I'm done. I don't think about it again. And it's a pretty small change to gravity, like 0.3%. Coriolis force I care about a lot and think about all the time. And then we finally get this set of momentum equations. And so I actually really want you to understand this set of equations. Like really, really, really want you to. Okay? That was a hint.
That sounds like a hint. Oh, sorry.
I don't know how much more I could say that. All right, so what do you think I want you to know about this set of equations? What did we do the rest of the course? Basically the whole second half of this course was
different combinations of these equations.
There we go. So what combinations do you recognize?
Pressure gradient force.
Yeah, so there's a pressure. So certainly if I ask you, which is the pressure gradient force, you should be able to point to it. Like I could ask you a question, circle the one that's the pressure gradient force. Good.
Coriolis for sure, the F.
So there's Coriolis.
Viscosity.
Yeah.
And
Right.
then the G that's only in the vertical.
Yeah. And what this one is?
Acceleration.
Yeah, it's acceleration, right?
In the north, south, east, west, and vertical, right?
So this is a convention for us, but it's such a strong convention, I'm going to stick with it. U is usually eastward, V is northward, W is upward. Okay?
Unless it's negative, then the opposite, right?
I'm going to try not to make you confused in this way, but I will stick with W being upward best I can. I don't want to make that a confusing point. It can, but I'll try not to on any test. All right, so those are the names of the terms. That's good. All right, so let me ask you some questions. All right, so say I tell you geostrophy. What's the balance? Which two terms?
Pressure gradient force and Coriolis force.
There you go. Bingo. Right, there we go. We spent a lecture on that. Okay, how about you? Tell me, what other two have we balanced? So let me say, what if I tell you the flow is steady, doesn't change in time? Which term can we ignore?
Acceleration.
Right. We could ignore that one, right? What if I tell you we're studying waves? Which term do we certainly need? Waves change in time.
Acceleration.
There you go.
Oh. That feels like a trick question.
That wasn't tricky at all. But that's the point, right? This is the point. Okay. So yeah. What other balances? We covered a number of them. Basically, you can take all of these, and you could basically form every possible pair, certainly among the ones that are not the acceleration. Like, let's do that. Form every possible pair, and you tell me which one it is. Okay, we did this one and this one, right? What's that? There's got three terms. Let's every possible pair. We got three. How many pairs are there?
I don't remember that one.
Come on now. Huh? If we have three terms and we pair them all up, how many possible pairs are there? There's this one and this one, this one and this one, and this one and this one, right? All possible pairs. We studied all of those, by the way, at some time or another. Okay, we did. We actually did. Okay, so this one and this one, that is?
Geometry.
This one and this one?
Is it wind?
Hold on.
Is it wind curl?
Wind stress,
Wind
yes.
stress.
Wind driving, yeah. It's like Ekman,
stress.
wind, yeah, there we go. Just because my computer's going to sleep, it'll wake back up. Wake up. Oh, sorry. It got logged out. There we go. Okay, so that makes sense though, right? Wind? We often put in a tau over here, right, for wind stress. We'll get to that. We'll cover wind again. What about this one and, yeah, this one and this one? You remember that? You don't have to think back very far in time.
It's a good clue.
Like very not far in time. Remember this one? So that's pressure gradient against friction, or wind stress. Well, it's often wind stress that's doing it. At the equator?
The up going down.
This is the mean balance at the equator. Remember the pile of water on one side, and that's causing a pressure gradient, and then the wind is blowing against it? Yeah, this is the mean balance at the equator. So that's really recent. And that's just, we just covered that on Tuesday. We actually did we did this balance, right? Those two. You had a homework problem.
Hold on.
Yeah. Yeah, inertial currents. That was the homework problem. In that case, we just took, remember this is a big fancy term with it, you know, d by dt plus u du dx plus v du dy, right? And we just took the first term, that's the linear term, basically, partial u, partial t. And we balanced that with these two equations, and you did the inertial currents. That was a previous lecture, right? I mean, previous homework, the one before this one, right?
Oh my God,
Yeah.
it feels like so long ago.
I know. That's a review. This is a review.
I
So,
think it
so
was part of like the extra credit or something.
no, that was, I think it was question one. Oh, we
Oh,
did?
yeah,
Yeah.
it
We
was
did?
question one.
Yeah, it was question one. Yeah, we did you're right about, the extra credit was actually this balance.
Yeah.
Yeah, for the Ekman spiral.
Ekman spiral. I do remember that one.
So, oh yeah, we haven't talked much about the vertical equation, but we certainly did this balance, right? That's hydrostatics. Yeah. I think that's pretty much what we did in the vertical for the most part. Okay, why am I going through this? The reason I'm going through this is pretty much every lecture after this one just considered different ones of these balances. So that was the idea. Then we talked a little bit here in this particular lecture about free inertial motion, right? That's the one we just said. We talked about geostrophy. I was kind of previewing. Wind-driven currents. Yeah. So this is the last slide of this lecture, and the reason I'm spending a lot of time on this lecture is pretty much because this is so central to so much of what we talked about. I need you to really remember and understand the things we just said. I will promise you there will be something on the final exam asking you questions like we just talked about.
What's the one called where it's balancing at the equator? Is that mean of balance?
When this balance at the equator, yeah, it's the mean, the steady balance at the equator. I mean, I don't know that it's pressure gradient against friction. I don't know if that it has a more of an term than steady balance at the equator, but it is the steady state balance at the equator. I think it's fair to say, with the big caveat that the equatorial flow is basically never steady. But this is what it would be to the extent it is. All right. Okay, any other questions about this? Okay, next one. Then we went on to geostrophy. Okay, here's geostrophy. How do you need to understand this? If these are lines of constant pressure, the flow in the northern hemisphere is such that it keeps the high pressure on the right of the flow. And the reason that works then is because then the pressure gradient force is exactly that way. The Coriolis force is exactly to the right of the direction of flow, and then the balance will be exactly Coriolis and pressure gradient. So that means flow follows exactly along lines, exactly geostrophic flow follows exactly along lines of constant pressure. At the surface, those would also be lines of constant sea surface height. All right, so then, this next, here's another try at explaining the same thing. And, one of the fundamental things I want you to understand is basically there's kind of a 3D, at least a 2D thing going on here, where you just have to keep in mind what direction things are, what hemisphere you're in, and I do want you to be able to do that. I want to be able to ask questions about, here's the field of pressure, what direction is the flow? All right, so here are the equations. We just talked about them. We talked about using, reading weather maps. So I think it would be fair game for me to give you a weather map and ask you to tell me what direction things are going based on what you see in the weather map. Same way, these are worth remembering as well. This is what at the surface of the ocean, the pressure gradient is basically due to the height of the surface. So you can write the geostrophic equations this way. And I think this is a really useful way to remember them for the surface flow in the ocean. Like a really, really, really useful way to remember them. Okay? So it allows you to do something that I think you should be able to do a kind of back of the envelope calculation of the numbers, say, typical of the Gulf Stream. Like these numbers, I think are worth remembering. So, like, what is it? Basically, this is the balance you have to have. So, if you know things like the latitude, and you certainly know G, right? If I tell you either delta H or delta X or V or any combination, you should be able to figure out the others. It's almost as if I tell you it's the Gulf Stream, I don't have to tell you anything else. And you should be able to do a calculation like this. So do those make sense? I mean, these are all actually pretty easy numbers to remember, certainly easy numbers to write on your little cheat sheet. But I remember these. So F is about 10 to the minus 4. I mean, this may be useful because I'll ask you to do a calculation of F. And in mid-latitudes, certainly, not at the equator, it goes to 0. But in mid-latitudes, a number around 10 to the minus 4 tells you you're pretty much there. G, you know that one already. Delta H in the ocean, about the biggest one you ever get, is about 1 meter. That's across the Gulf Stream. And the width of the Gulf Stream is about 100 kilometers. And one of the easy numbers to remember, at least for me, is the Gulf Stream's about 1 meter per second. So there's a lot of ones in there that are relatively easy to remember. All right, any questions? So let's see, there's lots of examples of, like this one. This is sea surface height. Here it's in centimeters. I think you should basically be able to look at this and at least tell what direction the flow is at any point on this map. Like really be able to do that. So, you should be able to do that anywhere on this map. You think you could? Point to a place. You'd say what the direction is, right? Should I point to a place? Sure. And that is, say it in words, because that's what you'll have to do on an exam. Finger won't work.
What if I drew the finger on the map?
I'll probably have something, yeah, there'll be some way for you to indicate it, but yeah. It might have to be in words, because it's an exam. Okay.
West.
Westward, yeah. Okay, how about like right there?
South.
Southward,
Southward.
is that right? Okay. How about right, let's go to another, to the southern hemisphere, right there.
South.
West.
There are a lot of options here. Yeah. So it's parallel to the line,
Yeah.
okay? So just, don't worry about the wiggles too much, right? So let's say this line is pretty much a north-south line. So that means it's gonna be either northward or southward. And it's the southern hemisphere. So what's the rule in the southern hemisphere? The high is on the,
Left.
so which direction is it going?
North.
North.
There we go. Okay, get the idea, right? I should point, we'll point anywhere. Let's point here. And let's say that we take these lines to be pretty much going east-west. So this is either gonna be eastward or westward, but which way is it?
East.
Mm-hmm. Going this way. Yeah,
East.
eastward. Okay, where else is a good place to look? How about right there? It's right there where yeah,
North. No, wait, no, south.
south.
Okay.
Let's go up into let's go like right here. So let's take that to be pretty much north-south line, okay?
North.
South.
And it's going to keep the high on the which side in the northern hemisphere?
Right.
Okay. And let's see, this is low and this is high. This is higher. I think this is lower and this is higher. You agree with me?
Yeah.
So
Yeah.
So it should be north.
North. So okay, should I guarantee I'll ask a question like this? Yes, I shall, guarantee. What form it will take exactly, you will find out, but it's going to ask for this level of knowledge. Okay? We can practice this as long as you want. So given that you can find all these different currents, they're all in there, and yeah. So thermal wind. Thermal wind is basically lets us know, it's a combination, what do you need for thermal wind? You need the geostrophic balance and the hydrostatic balance. You slap those all together and you find that the vertical shear of the horizontal current is related to the horizontal gradient of density. And then we were looking at sections like this, remember? Looking at sections like this. And here the key is that you kind of always say, well, let's suppose the flow is 0 at depth. The thing to remember is then the flow will be such in the northern hemisphere that the hot water is on the right. That's a way, so you don't have to remember, like I don't even know if it's helpful to remember these signs. There's a minus sign in this equation, but not in that equation. But here's the way to remember it. I hardly ever remember where the sign goes. I just remember that the hot water is on the right. Okay, remember this?
Sorry, can you like spell it out, like how you look at the equations and points to the right? What's the right side?
Oh, so how I get it from the equations?
Yeah, like what do you
Okay.
say when you say that?
Okay. So how do I get it from the equations? Okay, so let's look at, yeah, how do I get it from the equations? Okay, now I have to draw something. Let's see if I'm not a good artist, so here we go. Here we go. Huh?
You're a great artist.
No, I am Okay, so let's see, here we go. Well, maybe just instead of me drawing, let's just look at one of these examples like this one. Okay, and let's just use that one because it's a real example. Okay, so this is actually the Gulf Stream, and I think you can see there's a strong density gradient there, right? Okay, so this strong density gradient, and let's say that's an east-west section. Okay, so that's a gradient of rho with respect to x. Okay? And yeah, so it's going less in this direction, in the positive x direction, it's getting less dense. So d rho dx is less than 0. Okay, here we go. Let's go back to this. There it is. There's d rho dx. It's negative. So that's negative 2. So dv dz is positive. Got it? dv dz is positive. So that means positive is into the board. That's why there are these x's. Yeah. So hot is on the right. Good question. I mean, that's where it comes from, the math. But the thing I remember, I never remember those signs. They don't help me. If I'm just looking, I remember hot on the right. And if I'm doing it, where I have to do, solve the equations on paper, then I'll make sure I got the signs right. But yeah.
So doesn't that swap for southern hemisphere?
Correct. And the way it swaps is because f is negative. The value of f is negative in the southern hemisphere. That's how it swaps.
Okay, I'm a little confused because isn't positive towards u in a traditional three-dimensional XYZ graph?
Yeah, but wait a second, yeah? So but this is northward velocity. Got to think in more dimensions here.
Okay.
Yeah. That's northward, not eastward velocity. Yeah. Huh?
It can be a little confusing.
It can be a little confusing. I accept that. And that's why I'm trying to make these kind of ways to remember. And basically what geostrophy talks about is if you have a section in one direction, it talks about the velocity through that section, normal to that section. And we actually do this calculation all the time. It's really common for us to do.
So in general, if you see the density going up from left to right, you're pointing into the page.
Correct, in the northern hemisphere.
In the northern hemisphere.
Yeah, sorry, but you've got to remember what hemisphere. And so that's why, I had you do this problem where you drew it on, it was a kind of open-ended question and it seems odd, right? But the reason is I want you to draw it one time because I think by drawing it, it helps you to remember. And so please do refer back to that question. I think it's posted. Try to use that to help you remember. Could I ask something like this? Absolutely I could. Like I could give you a section and I could say what direction is, assuming that the flow. I'm not going to be too tricky. I'll say assuming the flow is 0 at depth, what direction is the flow shelf, right? I can ask questions like that. I should be able to get a reasonable answer, right? Yeah. Okay?
So
Feel
the
free to ask
flow is
questions, yeah?
always normal to the density gradient.
Exactly. Exactly normal, just like it's exactly along lines of constant pressure. You bet.
Are you gonna give us any tricks about not knowing if you're in the northern or southern hemisphere?
No. You will know. I will make it possible for you to know. Like you'll be able, what's an example? If I give you the map, right, and it's got latitude on it, you could read the latitude, right? Or even better, almost by now I'd expect you, are you pretty close to where you can see the Earth and then know where it is just from the outline of stuff? How close are you to that? Close? But anyways, I'll make sure that's not ambiguous. And actually, Megan, to your question, you asked the question, is it exactly normal to the density gradient, right? You asked that. And it's the shear is exactly normal to the density gradient. It's actually not the velocity, it's actually the shear.
Oh.
But I'm not going to go in. That's an actually very interesting detail. I'm not going to bother with trying to go into that little subtlety.
You mean the velocity component?
Right, it's actually the shear of v. dv dz is exactly normal to d rho dx. It's not that v is exactly normal to d rho dx. And there's an interesting little idea in there that is a little more advanced. But that is, for the purpose of this class, just remember it's normal.
Wait, not because of outside forces? There's like a reason why the force itself is not.
Well, this is exactly the thermal imbalance, and the shear is exactly normal to the density gradient. That's the truth, yeah. That's so far is the truth. But if the density gradient has some some structure, the velocity itself could not be normal to the density gradient. But we don't want to go there. All right, here's an example. Remember this one? So you can read latitude off this. And so does it make sense to you? So this is southern hemisphere. These lines are lines of constant density. Can you explain to yourself in your mind why the flow is out of the page there? So it's going to, in the southern hemisphere, let's assume flow is 0 at depth. It's going to keep the hot water on the left. So that means, so here it's hotter, here it's colder. Flow out of the page. Okay?
It's colder. I'm looking at the red
Oh,
46 and then.
yeah. So just look up here. These are actually density, not temperature. And what it means is lower density is higher temperature. See, the way I just remember it in terms of temperature. I think it's easier for me to remember it in terms of temperature. But there you go. All right, what else? So some explanations of, these were just tries to help you understand all these ideas, but the ideas are just what I explained. And then we get to, things like this. So here we go again. So if I use this, I could say, I don't know if can you read these from far back? I don't know. Can you? Like I might say, okay, so tell me about the North Atlantic current. Which direction is it going? Right. Yeah. Yeah. So I'm going to ask you questions like this. I don't know which map I'm going to show you, but I'm likely to show you a map. And then we'll go through that.
If you gave us a map, would it have all of the names on it like that? Or would you just be like, here's a map, find the south equatorial current and then tell me which direction it's going?
No, I'm not going to ask you, let me do this. I'm not going to ask you to remember names of currents and where they are. I think that's a lot. But if it has the names of currents, then I could tell you. Or if it has, I put like A and B and C on it and say go to point A or point B. Yeah, more like that.
I missed the answer to the last one, so it's clockwise? Is that the answer to where the North Atlantic current is
So
going?
there's the North Atlantic current. And so it's going to be parallel to the lines of constant sea surface height. So you got two options. It's that way or that way. And it's going to keep the high on the...
Right.
And can you read these? So blue is lower, orange is higher.
Okay.
And this actually does have the values on there in centimeters. Okay, let's see. I think we could do it again and again, but I actually won't be any better than you studying these on your own and being able to do that. Plenty of opportunities to come up with the kinds of questions I might ask. All right? I think that's it for geostrophy. How are we doing? How are we doing for time here?
30 in.
30 in, okay.
Is that right?
And we have 1, 2, 3, 4, 5, 6 to go. Okay, better pick it up. Better pick up the pace. All right, what's the next one? The next one is wind. All right, so first we talked about all the things about the atmosphere that any physical oceanographer needs to know. I think you should know these things, but I don't think I want to use a test question on the atmosphere. But I do think you should know them. But what you should know about them is kind of like how they affect the ocean. That's what you should know about them. So let's stop on this one. I think I've shown this. You know, do you notice there's certain things, certain maps I've shown about? Yeah, 10? Yeah, could be. I think I showed them 10 times because they're not important. I show them 10 times because I think they're probably worth reminding you, and I think repetition is a way to learn. So there we go. These are wind stresses, and let's go. I think you should. Well, for now, I think you should know certain things about the atmosphere. Where are the westerlies?
North, right off the
They're coming from
Pacific
the west.
Northwest.
Yeah, so where are they in this? Tell me where to point. What latitude band?
40. Yeah, 40.
With the red.
There? There? Trades.
Just
Blue
south of it,
beneath
the
them.
blue region.
There we go. Okay, so I think at that level I should be able to ask that kind of question. Okay, what else? What's next? Okay, I'm not going to ask you about Farrell cell. I mean, I didn't even Hadley cell or any of these. I'm not asking you about those. I didn't even do a good job of explaining them. You got to tell me after next quarter's class if you can explain them. All right, so here's this wind stress again. Now I wanted to get to this part. Okay, wind-driven transport. This is really important. Basically, the wind-driven transport, this is basically telling us, this is the integrated velocity. That's exactly to the right of the wind. Okay, what's the way to remember it? So it's to the right of the wind in the northern hemisphere and to the left of the wind in the southern hemisphere. That's how these signs work out. So that means if I give you a map of wind stress, you should be able to tell me the direction of the transport. Same kind of thing as with geostrophy, just for wind now.
But it's the transport that's to the right of the wind stress?
Correct.
You said? Okay.
It's the transport, you bet.
Wait, is that,
So this big V and big U, they're just the vertically integrated. This is basically a definition of big V. It's the vertically integrated velocity. From the surface down to some depth where the stress disappears. So a lot of stress at the surface, and the stress keeps getting transferred down and down and down until finally it gets so deep and you don't feel the wind anymore.
it's always to the right of the wind in the lower and southern hemisphere?
See, this is where it's in the northern hemisphere. So it's I should have put in the northern hemisphere. In the northern hemisphere. In the southern hemisphere, it's to the left.
I know I'm going to get this wrong again.
Why? Why do you know that?
Easy to forget.
Well, and then if this layer is if the velocity is uniform in the layer, you can actually write equations like this that relate velocity, depth of this wind-driven layer, and the wind stress. And I think I gave you some problems like that, right, in the homework?
Yeah.
Yeah, so you can review those, because I could ask that, right? That's straightforward enough. If I give you, if I tell you some of these, could you figure out the others, right? The similar to what I could do with geostrophy, I could do with wind stress. All right.
Is that negative sign fixed in that then? 'Cause
Yeah, that
we're
negative sign,
talking
yeah.
about it directionally.
Again, I'm saying the way to remember it is the transport's to the right of the wind in the northern hemisphere. That's what this sign means, these pairs of signs. That's what they mean. I'm gonna try super hard not to be tricky about this.
Okay, yeah.
That's not my
There's
goal.
so many ways to be tricky about
That's
this.
not my goal, is to be tricky about this. But I do want you to remember what direction it is, like to the right of the wind in the northern hemisphere, to the left of the wind in the southern hemisphere. I do want you to know that.
For the math stuff, I mean, like the much mirrored the homework problems. So if you like had your homework problems written down, you could pretty much get away with plug and play. Is it going to be the same thing for pump?
Well, I mean, I'm not trying to be tricky. That's all I can tell you. My goal is not to write an exam that you look at and it's all tricksters. You know, I'm not going to write questions that I hope that will be tricky. I hope they are questions that are straightforward. I hope to. That's my objective. So, and I'll be here to answer questions. If some part of the question seems tricky, you can ask me and I will answer. Okay, and then we talked something about Ekman pumping. So I want to go to now that we did that, I want to go back to this. Yeah, I want to go back here. Okay, now we've talked about where the westerlies are, where the trades are. Okay, so let's go to the westerlies. Let's for the heck of it, let's do the southern hemisphere. Westerlies, right? What direction is the transport in the ocean? The wind-driven transport. Northward, southward, eastward, westward. Northward. Northward, right? Okay.
I can't even see what direction the arrows are going in.
I know, I'm
Yeah.
sorry. Basically the red is telling you they're mostly going this direction,
Okay.
the blue is telling you that's what the colors are for, but good point.
Also, westwardly blow east.
Yes.
From the
It's
west.
like the worst day of his life.
I know, and I will try again not to be tricky about this, but hopefully, like, you could read this if this were printed on the piece of paper, you could read it. Hopefully. Okay, what about there? What are those called? The winds again? Those are the trades. Okay, and which direction is the transport in the ocean? Southward, right? What about right in between then? So the transports.
There's no transport.
Okay, true, that's true. If the wind is 0, there's no horizontal transport. But then remember about what happens next. If you have southward transport here and northward transport here, then right here the flow has to be downward. And that was what we called Ekman pumping. Right? Remember that? Remember about Ekman
Is that
pumping?
the cause of the gyre, or is that something?
Yeah, we'll get to that next. Yes, it is. Yes, it is. So that was this next part of the lecture, was we talked then about that there's Ekman pumping and it's related to the wind stress curl. You did have a homework problem. I think it's this homework. It was really about, it's about something we'll cover next. And we talked about how the wind stress curl matters, but I would really like you to be able to identify it. And then finally there's the Ekman velocity spiral. That was an extra credit problem that some of you did, but it's one of these features of the ocean that actually is visible. You can see the Ekman spiral, that the wind spirals beneath the wind stress. Okay, let's go to the next.
Divergence is pumping and then divergence is upwelling.
Yeah, it's Ekman pumping is downward, Ekman suction is up. Yeah. And so let's see, let's go to the next potential
Wait, when
vorticity.
you have Ekman suction, is it just the counter rotating the other way?
Oh, well, let's go back to the wind stress.
Because I feel like, wouldn't it always cause pumping?
No, wait. That's a good point. Let's look at it. Okie doke. Go to the subpolar gyre. So let's say like right up here. Okay, which direction is the Ekman transport underneath the westerlies? Southward. Which direction would they? The blue says it's mostly this way, so let's say it's exactly that way for now.
Okay, I see what's going on,
Then it would be northward, and then
so you have
here
this
there would be upward flow because there's a divergence at the surface. Good questions. Okay, let's see. Let's go on to the next one. Is potential vorticity. Okay, potential vorticity. Let's see. Potential vorticity. We talked about The relative vorticity, there's a review of the Coriolis parameter. We talked about beta, which has to do with the change of F with north-south position on Earth. It's about 2 times 10 to the minus 11. I'll say that I don't need you to memorize 2 times 10 to the minus 11. So maybe if I ask you to do something where beta matters, maybe I'll give it to you. And then we talked about the important thing in this lecture is that potential vorticity is conserved, and potential vorticity is defined to be the sum of planetary plus relative vorticity divided by h. This is potential vorticity in a column. And I remember I was doing a lot of trying to sell stuff, and you were actually buying until a certain point. But I got you buying for a long time in that lecture. Until a certain point, you're just like, no, I'm done. But
Money.
huh? But let me. One part I actually thought you were still buying at a certain point was this notion, since you know about angular momentum, and if you were to think of a column of fluid that's spinning, right? Like remember what, like a person spinning, you know, that their arms are out, spin slower, arms in, spin faster, angular momentum's conserved. Take a column of fluid and you stretch it up like this. It's as if arms come in, so it spins faster. Or you squish it down, arms go out because it's conserving its volume slower. So that's all potential vorticity is. That's just doing that on Earth with the extra rub. Here's the rub. The extra rub is that the spin of a column of fluid on Earth is due to both how it's spinning on the Earth plus the fact that the Earth is spinning. And so that's the rub. And I thought I had you buying it roughly through this point. I'll tell you when I thought you were no longer buying it. But anyways, what we could then do is think about, there's really just 3 terms here. We could think about balances between any 2 of them. And so we thought about if we had something that was just staying at the same latitude, so F is constant, then zeta over h would have to be the things that's conserved. And that's just what I talked about. This is just stretching that column or squishing the column and having it spin. I thought you were buying that. And then the other part of it is say that h stays constant, and all we do is move this column of fluid northward or southward. Then F is changing, so zeta would have to change just to make that sum stay constant. Were you buying that? I thought that was still pretty much a buy. And then finally, this possibility, let's keep zeta constant. In fact, let's just let it be 0. And then F over h is the thing that has to be conserved. And if F over h is conserved, this means that if we've got a column of fluid, you move northward, it's as if it's spinning more. So that's like getting taller. It's just as if the spinning skater, all the spinning skater has to do is not spin faster, just move on Earth. Still buying? I think so. This one is the one that is the approximation we use, that F over h is conserved. That's the approximation we use to then understand how the gyre works. All right, so we did this for a drip balance. You had that for one of your homework problems. Well, there's the wind stress again. And then we talked about how we could understand that the flow in the gyre is southward. And basically the way we could understand it is because there's this Ekman pumping in the gyre from transport northward under the trades and southward under the westerlies, there's downwelling that if you thought of a column below that, it's getting squished. So its h is getting smaller. So if its h is getting smaller, F has to get smaller too, so it's moving towards the equator.
So we have a lot of
Still
cues.
buying. Huh?
I'm just having another issue now.
Yeah.
We have a lot of cues.
Oh,
Will
I
the
see.
rest of the
I know.
context of the question
I
make that
know.
clear? Because the other cues were mostly about heat, right?
I know. I'm sorry. You're right. You know, when you're right, you're right.
But I mean, the other variables should kind of lend to letting you know what, and I'm sure the question should let you know which Q you're
I'll try to
referring
make sure it's not confusing by saying exactly what I mean, but it is true that in our field, we use Q for both. Bad on us, so bad. I don't know what to
I
say.
think all
There's-
physics uses
there's-
things interchangeably.
Oh, yeah, I mean, if you go throughout physics, you find variables used in many, in context, you have to know what it is, and you're right,
How in math and physics, they always switch phi and theta.
Yeah.
Oh, yeah.
Like all the math people will use phi as their angle from
Yeah.
from the pole, but all the physicists will use theta as their angle from the pole.
Oh, really? Okay, yeah, anyways, I will try my best. This is not the way I'm not gonna ask you what is Q. Okay? I'm not gonna do that. I'll say exactly what I mean, and I do apologize for that. I think we just run out of variables is the answer. There's just not enough.
You've already started with symbols, so it seems like if you're going to weird symbols, you might as well just keep running with it, but.
Well, there's the, yeah, anyways, there's all the Greek.
I get that's alphabetical too, though, isn't it? Yeah.
Yeah, and
that's
some of
fair.
them, the problem is some of them look too much like other things, and so you can't really use all of them. Like Omicron, nobody's gonna use Omicron.
I don't even know what that is. So.
It looks like an O.
Oh, no,
It's not helpful.
They do in differential equations. It's the what's it called? It's the order.
Yeah, fair
You know
enough.
how they say O.
Yeah, I know.
It's the order of term that's left out the remainder.
So, okay, so then we talked about sphere of transport. You don't have to just, I have the derivation there. I'm not gonna ask you to reproduce derivations. The notion behind the sphere of transport, I think, is worth knowing. It's just what we just talked about. It's if the wind stress curl is such that you cause a convergence negative, then you get this southward flow. That's what the sphere of transport's about. And then finally, we did this little argument about why we have the boundary currents on the west side of the ocean. That's what you need to conserve potential vorticity. I think you are no longer buying around this point. I sensed less purchase because it was a lot. And so maybe I'm not going to try too hard to ask you questions about those things. Then we talked a bit about Rossby waves. And maybe, I don't know if you started buying again, but Rossby waves are a vorticity wave. And we had a little explanation for why. I need to move on. We need to get this done. All right, what's next? Okay. And then we all breathe a great sigh of relief because this topic is way easier. And so now we're on to eastern boundary current systems. And basically all this is an application of ideas that you've already seen. That's really all it is. There's no kind of new ideas except that there is a coastal boundary. And then we pointed out where they are on the eastern boundaries. They're upwelling zones. Why are they upwelling zones? It's because if you look at, this map is showing both surface pressure in the atmosphere and the direction of the winds. And so what is the thing I want you to see is say, let's look at the Canary current system. The winds here are southward, so what direction is the flow in the ocean?
Eastward? Or west, I said. I
This
pointed
word?
in the right direction, said
Yeah.
the wrong word.
Yeah, I know. This way? I mean, I say the wrong word all the time. So, and then there's a boundary here, right? And there's no flow through the boundary. So if the flow is westward there has to be upwelling.
Upwelling.
That's what causes coastal
Suction.
upwelling. Yeah. So that's coastal upwelling. That's basically the fundamental idea here is that coastal upwelling, this is actually a review of the Ekman transport. Then there's a little bit of a review of Ekman suction because of wind stress curls also matters. And then that's all review, so I'm not going to review it again. But in the end, what does it all mean? It means that you've got flow offshore and upward flow near the coast, that is the coastal upwelling. That's what it means. That's it. That's what's up.
Is that the only cause of coastal upwelling?
Coastal upwelling is wind driven. It is caused by wind. I think that's fair to say. There are a couple aspects of the wind. There can be some wind stress curl that can contribute, and just the fact that there's wind and a rigid boundary that you can't have flow through, both of those contribute, but in the end it's wind. No wind, no coastal upwelling. Need wind.
And that's why the upwelling that's not against a coast is less significant, right? Because there's upwelling happening in other places, it's just not as drastic.
There are, and like for example, one of those places is the equator, and we
Right,
talked,
yeah.
we'll review that again, but that was just on Tuesday, yeah. So those are the places where there's, so the big upwelling tends to happen near the coast. That's the curl-driven part. What else is interesting? Basically, that upwelling causes blooms because it's bringing cold nutrient-rich waters to the surface. The basic picture is one like this. I think this is an easier one than the one I pointed out before, that there's offshore transport at the surface, onshore transport below. Got to have that to conserve mass, right? Because if we say no variation in this direction, flows that way, got it. Flow this way has to be balanced by flow that way. And then there's upward flow at the coast, and that's called the overturning circulation at the coast. For what it's worth, you want to hear? Do you want to just do review, or you want to hear something like what we're actually working on right now? Yeah, just for a second. So, from theory, we know the Ekman transport because that's some really solid theory. We know how deep it goes. We know the wind blows. We know the currents move. What we've always known less is what depth is this onshore flow? Because if I just know that this is going offshore, then I know enough water has to come onshore to basically to match that. But from theory, I don't know what depth that's happening.
So are you guys using like salinity as tracers, or what are you doing?
So we actually been running gliders for 5 years on this line off the coast, just back and forth, back and forth, back and forth, because these flows are really small compared to all the other things going on. So I'm averaging a lot to get rid of, to average out all the variability, just to figure out what depth this flow is coming onshore. We still haven't done it well, but I think we just did it pretty well.
No way.
And it's actually really shallow. It's all within the upper 100 meters, all this stuff. It doesn't extend very deep. Yeah?
So you were talking about how like the compensation for this change in height goes radially outward because you're using a cylinder. But over here, it looks like all of the change in area is happening away from the coast. When I could say otherwise, right? Maybe it's gonna also cause movement towards the shore.
I guess I'm not understanding your question. I'll try to answer
Like
it.
if I'm squeezing the disc of water down,
Oh, okay. You're
why
talking
isn't
about
it-
potential vorticity conservation. Yeah, I'm actually not talking about potential vorticity conservation right at this point in time. So all I'm talking about right now off the coast here is just that the wind is blowing. It would be constant. No variation in the wind, no wind stress curl. I don't need any of that. I just need wind blowing to make this go offshore. So for this particular argument right now,
Okay.
not right now, potential vorticity conservation. Yeah, questions?
So when they talk about nutrients coming up from the deep from upwelling, is the depth that starts at, is that where the nutrients are coming from?
Yes, that's why it's important to know. Yeah, absolutely.
It doesn't seem deep enough, right?
It actually is, and that's because this is all stuff I'm not going to test you on. Is it okay to talk about this? So yeah, it matters a lot because basically the nutrients, that's what's limiting growth of phytoplankton.
Right, yeah.
And so this was like the one time I talked about any biology, so we'll use all my knowledge. No, I know more. But so what do you need to grow a plant? You need
Sun.
light, nutrients, water, right? This is what you need on land. So if you're growing a plant on land, you need these things. Okay, in the ocean, what do you have? Okay, I'm going to say, just for the sake of argument, we got enough water. Okay, where do we have light?
Euphotic zone?
Yeah, euphotic zone, at some distance from the surface. Okay, so what happens is any available nutrients in many parts of the ocean get used up as soon as they're available because there's plenty of light there already. And so the surface waters tend to be basically stripped of nutrients. So what's the thing that allows growth is so deeper they're not used up because there's no light. So the phytoplankton can't use them. So upward flow basically supplies nutrients to the euphotic zone. And you get blooms pretty much
Right.
immediately.
And phytoplankton are the only species or animals, or they're not animals, I guess, but using those nutrients
plants.
specifically?
Well, they're the ones who photosynthesize, so yeah, they're the plants. Yeah. So basically, it is a really important question, how deep is this? But it can be pretty shallow because the euphotic zone is pretty shallow. The euphotic
That
zone
makes-
doesn't go
that
any
makes
deeper
more
than
sense.
100
Okay.
meters.
In my brain, I was thinking it needed to come up from, the abyssal plain or something in order to.
And that's a fair thing to think. You know, it might be, right? But it actually is you go down, tens of meters, you get down deep enough, and you go through what's called the nutricline, and there is
makes
much
sense.
more nutrients.
And don't things tend to travel in striated layers anyway? Like it would be on an isopycnal layer or something?
Yeah, it would be on an
regardless?
isopycnal layer.
Okay.
So, good, let's go on to that. All right, so here are the isopycnals. The black lines are the isopycnals. The colorful shading is the temperature. Because of this upwelling circulation, it tends to cause the mean isopycnals to tilt upward towards the coast. Because they tilt upward towards the coast, I'm not going to do it again, but we got geostrophy, got thermal wind, and so we talked about how that works as well. I'm not going to do that again. We've already reviewed that. And yeah.
So where's the high for all of these offshore, where's the peak of the water end up? So you have all these shores like pushing water towards a center, I guess? Is the middle of the ocean just like this peak of?
Oh, so this water's going offshore and all that?
Yeah, where's all the water converge to in this like big
It's not
smooth
happening
picture?
on both boundaries, right?
Here, let's get here. All right. All right, so basically, I mean, if I had the winds over the top of this, remember we talked about how the gyre, that's where there's a convergence because of wind stress growth. It actually is a convergence. So there is actually, look at these numbers. There's a pile of water in the middle of the gyre. So yeah, there is a pile. And that pile is also where stuff on the surface converges. And I think we mentioned this at some point, the whole thing about the Great Pacific Garbage Patch. I mean, it's actually real. It actually is real that stuff that's floating collects in the gyre.
So what's the height difference between the middle of the highest
Oh.
point of the gyre and the lowest point of the coast?
So yeah, these are numbers in centimeters. So there's 80. There's 0 right there. 0 is pretty much at the coast. So it's about a meter. I mean, remember we talked about a meter? A meter is pretty much what it is. It's a meter across the Gulf Stream in a short distance, and then it's a meter then all the way to the coast, to our coast, to the eastern boundary.
Not enough to surf on.
A meter?
Not enough of a
A
great.
meter's a big wave.
A meter, that's a meter
Big wave,
over, thousands of kilometers. Yeah, you'd be hard pressed to see it, wouldn't you? But it's important. It's what drives the ocean currents. Okay, yeah, so let's move on. I think I gotta keep moving here just to get this done. We're already at what time? 3. We gotta hurry up. We've got 3 more to do. But we also have sections, so we do have time. All right, governing equations again. This is about waves. What was the thing about waves? What is the, here's also, so the governing equations are all the momentum equations plus conservation of mass or volume. For waves, the thing we gotta have to have is the time derivative. Otherwise it can't move. All the others we may or may not have, but for sure we're gonna need the time derivative. So here's the linearized equations. By linearized, that means from the material derivative, we just keep the partial derivative with respect to time. Those are the equations. In a real class on waves, you learn how to solve these. So we don't do that here because there's only one period. I just tell you to remind you what wave solutions look like and to give you to dispersion relation. And there's the dispersion relation for gravity waves on the surface. It relates frequency to wave number, and that's g is acceleration due to gravity, h is the depth of the fluid. I think it's important for you to remember the dispersion relation for deep water waves and shallow water waves. I think it's very, very important for you to remember the dispersion relation in these two limits. What determines these limits? So the words deep should help you, right? It has to do with this parameter, kh, whether it's big or small. Because here's what you need to know about the hyperbolic tangent. If this is big, you're out here where it goes to a constant. If it's small, you're in here where it's kind of linear. Okay? I don't need you to be able to calculate the hyperbolic tangent in an exam. I hope that's okay. But I do need you to know that that parameter kh is really important, and knowing whether it's big or small leads you to these two possibilities. I do need you to know that.
It's a very common chart in population.
Yeah. So I do need you to know these dispersion relations. Did I say that enough times? Okay, yeah, I do need you to know these.
Noted.
Yes. So there's a variety of ways you can write them, but then I need you to know the phase speed. So the phase speed for shallow water waves is particularly easy to remember. It's a constant. It's square root of gh. If all you remember is g and h matter, you can pretty much figure this out by units. And then the deep water waves, there you go. If all you remember is that g, k, and omega matter, you can almost figure that out too. But anyways, you got your cheat sheet. So that's the phase speed of deep water waves. So I think I should be able to ask you a question as if, if I give you a wave of a certain frequency and I tell you it's a deep water wave, what's its phase speed? Something like that, right? Or if I tell you the wave number is this or the wavelength is this, and you got to remember the connection between wavelength and wave number, right? You know how the 2 pi works, and I'm not going to go over that again. That kind of stuff. Yeah, that kind of stuff. You have a homework problem on that now, right?
Mm-hmm.
That I think is good practice for what I could ask on an exam. Knowing that, like, you can actually fill in this table. Like, I tell you a couple things, you could fill in this table. So you should know how to fill in that table. Like, if you want some more, like, practice things to do, fill in the table. Like, just say, okay, here's my question. I'm telling you a period of 3 seconds. Tell me the rest. Like, that's all just from the dispersion relation. So that's all, this is just a whole bunch of practice problems right here if you take them that way. Particle motions are circles. I think we talk about this also in the homework. Basically takes a period to go around that circle. If you know the radius of the circle, you could figure the speed of the velocity, the particle around the circle. That's a homework problem right now. Anybody try it yet? Nope? Okay, let's do tomorrow.
No, we do.
You've had it for 3 weeks, so it's all right. It's
That part
okay.
confused me. I did most of everything else.
Okay. We talked about wave beating. What do I need you to know about wave beating? That it basically is caused by waves of slightly different frequencies, and I told you about how I remember it. You know, it's like if you ever watch turn signals on cars. You know how they go in and out of
You
phase?
said windshield wipers, I think.
And
right?
windshield wipers too, yeah. Yeah. All right, so then we talked about dispersive and non-dispersive waves. So for non-dispersive wave, that's one where the group and phase speed are the same. A dispersive wave is where they're different. And we talked a little bit about that. We talked about wave generation by storms. We talked about you have a problem where a homework problem where you're going to do this. We talked about how you can use the arrival of different frequencies to figure out how far away a storm was. And we finally talked about waves hitting the beach. So a lot of ideas in here that, you know, I think you should know. Okay, let's see, what's next? Now we're getting to stuff that we've done more recently. So I think right before Thanksgiving, we talked about tides, and we talked about basically the fact that there's this daily inequality. Typical tides can be either semi-diurnal or diurnal. We see a lot of semi-diurnal, that means twice a day. But there's springs and neaps, because this is basically, this is a tidal record off of La Jolla. The springs and neaps, that means like every 2 weeks there's a spring, and then in between there's the neap. And there's 2 peaks per day, one's bigger than the other, both high and low tides. And basically for tides, I need you to basically understand why there are tides. That's because that the pull of either the sun or the moon on the earth is slightly different on the close side of the earth to the far side of the earth. We talked about the tidal generating force and how that's proportional to r to the -3, where r is the distance between the earth and the moon, or the earth and the sun. And then we talked about the semi-diurnal tide, why there's 2 bulges, because it's the pull's stronger here and weaker here. That causes the semi-diurnal tide. We talked about the diurnal tide. That's because, say, for just the moon is not exactly in the equatorial plane, it's off. So that means if you're on a place on Earth, you get 2 high tides per day that are different in magnitude. I need you to understand these ideas. We talked about lunar and solar tides, and because of the r to the -3 dependence, basically we live in just an amazing place where both the sun and the moon matter. And so that's pretty cool.
Is the other side of the bulge being caused by the sun?
Back to this one?
Yeah.
Like, just start here. No. The answer is no, the sun's not necessary for this.
So wouldn't you expect there to be a egg shape for the oceans? Because the moon is much closer and the gravity changes with r squared.
Oh, well, that's the r cubed. I mean, that's when I do this Taylor series expansion. And so the first term in it, anyways, just the first one, has got this r cubed dependence. So that means more pull on one side, less on the other. So it makes this kind of elliptical thing.
But
I
that
don't know
image
that
is
if
wrong
you
then,
call-
because it shows that they sort of have the same heights.
You're
on
saying
both.
they're symmetrical on the
Yeah,
other
but that's the
side?
difference is the r cubed. The r cubed is the difference between this one and this one.
Okay, so that picture is not symmetric.
It is. I think it's fair to think of it as symmetric. Yeah, it is. At this level of approximation, yeah. Yeah, I think it's fair.
But why isn't all the water on the side of the moon?
Yeah, this is the classic question. Well, because it's pulling harder here, but it's pulling less here. So this is actually, and it's pulling the Earth at somewhere in between. Right? It's pulling this at somewhere in between, more on that, less on that, this in between. So yeah, the way to think of it, it is fair to say, the way to think of it is bulges on both sides. Yeah, at the simplest level, yes. So let's see. What else do you need to know? How does the Earth and how does the moon and sun both matter? That's what leads to spring and neap tides, because when the sun and moon line up, then these bulges are even bigger. So that gets you spring tides. And when they're out of phase, like during the quarter moons, that's when you get neap tides. And this kind of stuff, this is the level at which I want you to understand it, and which I would ask questions. I give you questions like this on the homework. So yeah.
It's pretty neat.
Yeah. I think so. Yeah. Still bugging you.
If you, well, no, that part makes sense actually. That
Okay.
there's less gravity, so if you move
Yeah.
further, that makes sense. If you drew a chart where you combine diurnal tides and neap and spring tides, you end up with like 9 different possible configurations or something.
So I mean, actually, you're getting to an important point, and I think this is the very next slide. Okay, here's where you get, this is why tides, even when I started, tides were not a topic that we spent a lot of time on. It's because a lot of it is about the orbit of the sun, of the Earth around the sun, and the moon around the Earth, and there's all the eccentricities and all the details, and they all matter. And then, so if you can actually look it up, go ahead, have fun, and Google tidal constituents, and it fills this page and off the bottom, and because we know a lot about all those details. So if this were a real course in tides, the first part of it would all be about all the details of our solar system, basically our solar system. Actually, other planets don't matter. The Earth, the moon, and the sun, and how our Earth rotates, by the way, because the speed of rotation, that's important. Because like, just say the moon's just sitting there, then it's the Earth rotating, the bulb stays in the same place, right? So it's how our Earth rotates, and so it's also about variations in the rotation rate of the Earth.
And I think I watched a video once that also has to do with how many times the Earth rotates cyclically when the moon rotates around the Earth as it goes around the cycle.
bet.
It's not even. It's not like there's
Yes.
It's not like for every one cycle around the sun, there's 10 moon cycles. It's like 10 point.
Yeah.
So it makes it very annoying.
Just
So
like
this changes.
constituent after
I think it
constituent.
changes is what they're trying to say. Like
Yeah.
these numbers change.
And it's actually so this is the whole system, right? And we've got the Earth is rotating. It's going around the sun. The moon's going around it. It's causing the tides. The tides are dissipating. They're moving. They're water that's moving. They're rubbing on the Earth. They're losing heat. So actually, this whole system is slowly spinning down, and in the fullness of time, it will come to a halt. Well, probably past whatever is going to happen to us, but the Earth is slowing down, and one of the contributors is the tides. All right, let's see what's next. We talked about the dynamic tides, and the dynamic tides are basically due to the fact that the tide moves as a shallow water wave, and we did this calculation in class. Do you remember? Whoever was in class that day? We did this calculation where we said, okay, it's a shallow water wave, it's in the ocean, the ocean's 4,000 meters deep, therefore I know how fast it is. What is it, about? 200 meters per second?
It is,
Yeah, and then you can figure out how long that takes to cross the ocean, and it's kind of on the order of a day. So it's just the same as the way the tides are forced. It's a near resonant forcing. And so the dynamic tides are super interesting. They're traveling like a Kelvin wave, which is a shallow water wave that leans up against the coast. And we talked about tidal phase and amplitude. So it'd be nice if you could understand how to read those plots. But yeah, that's the level at which I'd like you to understand things. And what is worth remembering, I think it's worth remembering how the Earth's rotation matters, how that sets the semi-diurnal, how the moon and sun matter, and I think I could ask questions on a level similar to the ones that are in the homework. Okay, next. All right, last lecture of this was just on Tuesday. How much review do you want? You want review? No?
Whatever is in this is on the exam.
You can also just.
Okay, well, let's see. Let's talk about a little of it. Okay, let's look at the wind again. All right, wind. So this is blue, so the wind is going that way. You can hardly see the arrows, but they're heading this direction to the west. Okay, at the equator, north of the equator, F is positive, so which direction is the flow caused by the wind? North. South, which direction is it?
South.
So what's got to happen at the equator? Upwelling. And if I gave you the wind stress, you should be able to calculate that. If I tell you F, and I tell you just off the equator and F, and just off the equator of wind stress, from what you know about wind stress forcing, you should be able to calculate that, and you should be able to calculate the upload. Right? I think you should. All right, so what else did we learn about? We looked at these sections. I'm not going to, I just did this 2 days ago. Yeah, so this was that steady balance. Looks like in this version, one of those, the new got mangled into an N-looking thing. All right, we talked about the momentum balance of the equator. We talked about El Nino. You can look at that video again. I don't want it. I just did this like 2 days ago. I'm not doing it again right now. I got nothing better to say. Except this was one of those lectures where we brought ourselves right up to date. And yeah, and so it's something we do right now every day. And our work off California is largely to look at the local effects that are driven by El Nino. And there we are at pretty much, what time is it? I got 3:16. There you go.
Good job. That was impressive.
Thank you. That's it. That's it for this course. I could use any final questions. Happy to answer them. I'd like to take a couple minutes for my throat, and then we can come back and do homework or whatever for section. Yeah.
Can you make sure the recording's on for the section too?
It is. It should be. I've been checking.
Yeah, it's been on. Yeah, it's been on.
There's the 10-minute gap, I believe.
Yep.
I just want to make sure because I have to go. Sorry.
Okay. I mean, we can wait if to keep it all on, we'd have to wait the full 10 minutes, and then it can start right at 3:30. That's okay with me. I could use at least 5 minutes. Any other questions? Okay, I will send a reminder at some point about the final, but you get your 1-page cheat sheet. You can write whatever you want on it. All I ask is that it's your own handwriting. You don't just print it up and then shrink.
Bring a magnifying glass.
You know, basically bring a magnifying glass. Yeah, just your own handwriting. That's all I ask. Okay, thank you.
Is it both sides?
Both sides, yes. That was true in midterm, right?
Yeah.
Oh, did you only use one? Okay. Well, yeah, both sides. Both sides are fine. But and then just fun. You know, you've asked it, but I will answer again. Anything covered in the class is fair game. It's not just on that second half of the course. I can't believe they erased some of our stuff to like do that.
No.
They just erased yours.
Yeah, just the stuff in the middle.
They must not have known it was about
The
turkey.
yeses and no's and
Oh,
And your,
and
your
the,
vote.
yeah.
They should have just erased it all.
I just erased what they did.
Of course, Kyle, the contrarian. I know, wasn't even here.
But Marissa won and shared the donuts.
What a good champ.
And she thought she was gonna lose.
I really thought more people were gonna come in and say they didn't like it.
That's what I was thinking too. So I voted 63.
I can just be thankful not everyone did it.
Well, I also
That
thought
worked in
like,
my favor.
I also thought like maybe not everybody eats turkey or is having turkey. So technically that's why I said no. I love turkey.
I love
But
turkey.
I can't say that I enjoyed my turkey this year because I didn't have a turkey.
Yeah, that's
Fair enough.
So
I think you stand alone in that. But
Yeah.
maybe you just haven't
Had
had
a
a
good
good
turkey.
turkey
I
yet.
have different turkeys every year.
Yeah, I
Like,
actually,
I
a
feel
lot of
like-
people don't like turkey.
Really?
Yes.
Yeah. There's so many.
Because it's
like,
dry.
Maybe I just,
Most people I know
not
Dark
if it's
meat's
cooked
good.
right.
yeah,
Yeah.
right, yeah.
Like most people